Okay, today we are talking about section 1.7, which is all about exponential growth and decay. The first thing we're going to do is recall that we have two different expressions. So two different expressions for an exponential function. Remember, we have the general expression and the continuous expression. Our general looks like p is equal to p naught times a to the power t, and our continuous looks like p is equal to p naught times e to the rt or kt. You'll see p naught is equal to e to the rt. Alright, so sometimes you'll just have a different variable in there. Either way, the k or the r are both the continuous rate, growth or decay rate. Okay, so now that we have recalled that bit of information, we're going to look at example 1. So we have suppose that $6,000 is deposited into an account paying interest at the nominal rate of 2.7% per year. Find the balance after 5 years if the interest is compounded A, annually, and then B, continuously. All right, so we're going to start with $6,000 in the bank account, and our rate is 2.7%, and we are interested about the balance after 5 years, and we have two different ways to compound this interest. Okay, and the reason that these two different ways is important is because we have two different ways of expressing our exponential equations. So for the annual compound interest, we are going to use the general expression. So our p is equal to p naught a raised to the t power. And for our continuously compounded interest, we are going to use our continuous expression. Makes sense, right? And I'm going to use RT in this case. Okay, so let's come back up here just to look at annually for a moment. What is our P naught? Well, P naught is the amount of money that we are starting with, which we were given as $6,000. Okay. Our rate is 2.7% per year, but remember, we always express our rate as a decimal. So the rate is 0.027. All right, percent just means per 100, so we divide our 2.7 by 100 to get this. And A is always 1 plus or minus r, right? Depending on if we are increasing or decreasing. So in this case, our interest is being compounded. That means it's being added to our previous amount of money in that bank account. So we are going to be increasing. So we're going to choose positive r. So A is 1 plus 0.027, so we get 1.027. And now we have all of the pieces that we need. So P is equal to P naught, which is 6,000, A, which is 1.027 raised to the T. Alright, so we found the formula, but the second part of this question asks us to find the balance after 5 years of sitting in this bank account. So we're going to go ahead and plug in 5 for t. Alright, so we get 6,000 times 1.027 raised to the 5th power. Alright, and if we plug this into a calculator, we're going to get $6,854.94. I'll go ahead and add a little dollar sign there. Alright, so this is our balance. Our balance after 5 years. As you can see, we deposited $6,000 originally, and we have now accumulated $854.94 of interest. Okay? Now let's come down here to part B, where we're going to look at the continuous model. All right, so again, we still have P naught is equal to 6,000. We still have R is equal to this 0.027. And E is what we already know. E is our approximately 2.71. We can just write it as E, so we have no more unknowns. So we have P is equal to P naught, which is our 6,000. We're going to leave E in here just as E itself, raised to the 0.027 times T. Those are all up there in that exponent. And again, we want to find the balance after 5 years. So P of 5 years, that's our 6,000, times E, raised to the 0.027 times 5. And a calculator will tell us that we now have $6,867.22. All right, and this is our new balance. So our balance after 5 years, if our interest is compounded continuously. All right, so if you had the option to choose if your balance was, or if your interest was compounded annually versus continuously, which one would you choose? I would assume we would all choose continuously because it looks like we're going to get a few more dollars out of it in the long run, right? All right, let's move on to example 2. In this case, we have Jordan's parents who would like to invest some money to help pay for his future college tuition. Their bank will pay interest on their investment at a nominal rate of 4% per year. So part A says if the interest is compounded annually, how much should Jordan's parents invest in order for the account to have $24,000 within 18 years? All right, let's highlight the important things again. So we have 4% is our rate, and Jordan's parents would like to have $24,000 in 18 years. They want to know how much should they invest. How much should they invest? Well, this is our P naught. This is our initial investment. Okay, so we need to find that out. We're going a little bit backwards in this case. All right, so we are also compounding annually, which means we're going to use our general form. So we have P is equal to P naught A to the T. Okay. We know that our rate, let's see, I'll write all this out. So our P naught is what we don't know yet. We know our rate is 4%, so that's 0.04. Again, we are gaining interest, so A is going to be 1 plus R. So we'll get 1.04. And we know that T is our 18 years. What is the last thing? The last thing we need is the amount we're going to have after 18 years. That's going to be our $24,000. All right, so now that we have all of our variables listed here, we can go ahead and plug them into our equation. Give me a little bit more space here. Okay, so P is 24,000. P naught is what we don't know yet. A is 1.04, and T is 18. All right, so let's go ahead and solve for P naught. So we have 24,000, is equal to P naught. 1.04 raised to the 18th power is going to give us 2.03 if we round up a little bit. All right. And then we divide both sides by 2.03. And we get P naught is equal to $11,846 as an initial investment. All right, so if we wanted to double check this, we could plug this into our original equation and see if we get $24,000 after 18 years. All right, but Jordan's parents would need to start with $11,000, or $11,846. All right, in this case, we're not including change. Okay, so what about if they were investing their money into a bank that compounded continuously? All right, so this is our continuous version of the equations. So we have R is still the same. That's our 0.04. T is still 18 years. P naught is still the question. And P is our 24,000. And we just need to plug all of this into our new equation. Again, I need a little bit more space. So we have $24,000 is equal to P naught times E raised to the 0.04 times 18. All right, so we'll get $24,000 is equal to P naught times 2.05. All right, go ahead and divide both sides and we'll get P naught is roughly equal to $11,707 as an initial investment. All right, so in this case, Jordan's parents would only need to have $11,707 to get started on their investment and still have $24,000 in time for Jordan's 18th birthday. So in this case, they will only need about I'm just going to roughly say $140 less to get started, and they'll end up with the same amount of money in the future. All right, so for example 3, suppose an investment decreases by a total of 30% over a period of 10 years. At what annual percent rate is this investment decreasing? All right, so we know that our investment is decreasing by a total of 30% over 10 years. And annually, so we know we're looking at our general formula. Okay, let's see what we are given. So we're given T is equal to 10 years. And we know that it's a total of 30%, but that's not our rate. And we are asked to find our rate. Okay, so we're not given the rate. So that means we can't find A. We're not given an initial investment. And we're not even given a total value that we'd like to find after 10 years. All right, so it doesn't appear that we're given much information at surface level, but let's take a deeper look. Suppose that an investment decreases by a total of 30%. All right, so instead of saying question mark, let's say that our initial investment is our initial investment. Some number P naught. We know that by the end of this, what we should be getting out of here is going to be 30% less than what we started with. So we're starting with our initial investment, and we need to subtract 30% of our initial investment. Okay, pause for a second, make sure you understand how we came up with this. All right, so if we are decreasing by a total of 30%, that means whatever we started with, we're taking 30% off of that. All right, so we should end up with 70% of what we started with. Okay, so let's go ahead and try to plug this in and see what we get. So we have our 0.7 times P naught on our left-hand side is equal to P naught. We don't know A, that's what we're trying to find, but we know that our time is T, or 10 years. We can go ahead and divide both sides by P naught, and look at that. It doesn't even matter what our initial investment started as, because it doesn't play into our equation. It cancels itself out. All right, now we're dealing with an exponent over a value that we don't know. There's a few different ways that we can handle it. I'm going to go ahead and take the natural log of both sides. Since we just spent a whole chapter learning about the natural log, I figured we could use it some more. So I'll take the natural log of both sides of a raised to the 10th power. And why did I do this? Well, so that I can bring that 10 out in front as one of our properties of the natural logarithm. We're still trying to solve for a, so we need to get it all by itself. So I'll divide both sides by 10 is the natural log of a. A little bit more space. I'll go ahead and put this into a calculator, and I'll get negative 0.036 is equal to the natural log of a. And we need to undo the natural log, which we know we can do by raising it to the base e. So we have to do this to both sides. Basically make everything an exponent now, but with the base e. All right, so we did this so that we could cancel out e in the natural log. So we get e raised to negative 0.036 is equal to a. And a calculator tells us that means a is approximately 0.964. All right, so we're getting closer. We're still asked for the rate, and we know we find a using the rate, right? We find a, ooh, crazy pen. We find a usually doing 1 plus or minus r. All right, in this case, we know that it's going to be 1 minus r because we know we are decreasing. We were told that in the problem. And we know that a is our 1.964, so, or 0.964, excuse me, is equal to 1 minus r. We can go ahead and subtract 1 from both sides. We'll get negative 0.036 is equal to negative r. And we like things to be positive when they can, and I'd just like to switch the order here. So r is equal to 0.036. And if we go ahead and write this as a percent, that means we have a 3.6% decrease annually. So no matter what initial investment we started with, we can still do all of this figuring and find that we have a 3.6% decrease. All right, so I have some definitions next for us. The first one is the doubling time. So we have the doubling time, aptly named, of an exponential function of an exponentially increasing It's important. Quantity. It is the time required for the quantity to double. Alright, so if you started with 5 of whatever, and you want to know how long will it take you until you've doubled, so how long will it take you until you have 10 of whatever unit you're dealing with. Alright, so that's the doubling time. And then we have the half-life, which is essentially the halving time, but we call it the half-life. So the half-life of an exponentially, this time decreasing function or decaying quantity, well, that is the time required to be reduced by a factor of 1/2. Of 1/2. So again, if you started with 5 of something, the half-life would be how long it will take you until you only have 2.5 of that thing. Alright, so example 4. I put a little hypothetical situation in here just so you know there's not actually a new virus discovered at USC that I'm aware of. Alright, so hypothetically, a new virus was discovered in the biology department at USC. Scott was a rather clumsy lab assistant who spilled hot coffee on his professor, who then threw the vial containing the virus, shattering it on the floor. So the group of 15 people in the lab were infected quickly, and only 7 days later there were already 94 people infected. Alright, I'm sure we've all heard a lot about how this works recently. So, assuming that the spread of the infection satisfies an exponential model, find a formula for the number of people infected t number of days after the outbreak began. Alright, in this case we are expecting everyone to be continuously infected. Alright, so we're going to be looking at our continuous model. Okay, so we know that our original group of infected people was 10. And we are looking for t is equal to 7 days after the incident. And we know that 7 days after the incident, we have 94. I'm going to say p of 7 is equal to 94. People infected 7 days later. Alright, so we want to find the rate. Alright, we need to find the formula, and that includes finding the rate first. That's what we're missing here. So let's go ahead and plug in what we know. We know p of 7, well that's 94. And we can go ahead and plug this into our equation. So that's our p naught, which is 15, times e to the r. We don't know what r is, but we know t is 7. Alright, so we have 94 is equal to 15e to the 7r. We can go ahead and divide both sides by 15. We get 6.27 is equal to e to the 7 times r. We'll go ahead and take the natural log of both sides. So we have natural log of 6.27 is equal to the natural log of e to the 7r. And we like to use that property to bring down the exponent in the natural log. So we have 7r times the natural log of e, which we know the natural log of e is just 1, right? Make sure that looks like a 1. There we go. So we can go ahead and divide both sides by 7. So we have the natural log of 6.27 over 7. Well, that's going to be our R value. So a calculator says we get R is 0.26. So if we want to plug this into our equation, P is equal to 15 e to the 0.26 t. And that is the formula for the number of people infected t days after the outbreak. All right, part B asks, what is the doubling time of the number of people infected? So, the doubling time, if we remember our definition, is just how long, in this case, how many days, is it going to take until the population of infected people has doubled? So, if we're looking at P is equal to P naught, e to the RT, well, we know that R is 0.26. We just found that. Okay, we know that P naught is 15. So we're trying to find T. We don't know how long it's going to take yet. That's part of the problem. What is P? So what are we planning to end up with? Well, it's in the name, the doubling time. We want to know how long it takes to get twice as many as we started with. Twice as many as we started with. 2 times P naught. All right, which in this case is 2 times 15. 2 times 15, which is 30. So we have enough information. We can go ahead and plug this into our formula and solve for time. So 30 is equal to 15 e to the 0.26 t. Right? We only have one unknown variable. So divide both sides by 15. We'll get 2 is equal to e to the 0.26 t. Again, we'll take the natural log of both sides of e to the 0.26 times t, so we can bring that exponent down. So we have the natural log of 2 is equal to 0.26 t times the natural log of e, which again, we know is 1. So we can divide both sides by 0.26, so we have the natural log of 2 over 0.26. That will be our t value. So a calculator tells us that t is 2.67, not years, days. There we go. Units are very important. All right, so in just a little bit over 2.5 days is how long it's going to take to get from 15 infected people to 30 infected people. That is our doubling time. All right, and this is our last example for today. So example number 5, a can of mountain condensate has 55 milligrams of caffeine, which leaves the body at a continuous rate of 14% per hour. So we have 55 milligrams of caffeine. We are leaving the body and at a continuous rate of 14%. Part A, write a formula for the amount of caffeine left in your system t hours after you drink 1 can of soda. All right, so in this case, it specifically asks us to use A instead of P. So we're looking for A is equal to A naught e to the RT, our continuous rate, right? All right, so R is equal to the decimal version of our percent over here. So we have 14%, so that's 0.14. And we are leaving the body, so this has to be negative, right? Negative R. And we are starting with our A naught is 55 milligrams of caffeine. So our formula for how much caffeine is left in the body is A is equal to 55 times E raised to the 0.14 times T. All right, that's our formula. And part B asks us to find the half-life of caffeine. So again, we know that R is this negative 0.14. We know what A naught is, but in this case, we don't really need it at the moment. But the half-life of caffeine, so that's A, well, that's going to be 1/2 of what we started with, A naught. All right? And you could use this as a decimal if you wanted to, 0.5 of A naught. It's just half of what we're starting with. You could plug in 55 for A naught if you wanted to, but I'll show you in a moment. It's similar to finding the doubling time, where it doesn't matter what we start with exactly. All right, so again, we have A is equal to A naught, e to the RT. But A is 0.5 times A naught is equal to A naught E. We know what R is, 0.14 times T. All right, and just as in our doubling problem, we can just go ahead and divide both sides by A naught, and therefore it cancels out. So this is where I was saying you could go ahead and put 55 in for your value of A naught if you wanted to, but it's unnecessary at the moment. All right, it would get you the exact same answer at the end. So we're going to go ahead and divide by A naught. So we'll get 0.5 on the left-hand side is equal to e raised to the negative 0.14 t. Same process, we'll just go ahead and take the natural log of both sides. So we have the natural log of 0.5 is equal to the natural log of e to the negative 0.14 t. We did that so we can use that wonderful property of bringing down that exponent and making it a coefficient. So we have negative 0.14 t times the natural log of e. We know that the natural log of e is equal to 1. So now we have the natural log of 0.5 is equal to negative 0.14 times t. We are solving for t, so we're going to go ahead and divide by negative 0.14. And that's going to give us that t is approximately 4.95. Is this in hours? Leaves your body per hour. Yes. T is hours. All right, so what does this tell us? The half-life of caffeine is roughly 5 hours. And a fun fact, I did Google this to see if it was anywhere near true, and Google says that the half-life of caffeine is 5 hours, depending on the person. So I thought that was pretty neat. Anyways, thanks for watching. This is the end of section 1.7. Don't forget to take the comprehension quiz, and I'll see you in the next lecture.